This is problem 8-150. It's on page, let's see, 457. Looks like I'm off the screen a little bit. There we go, that should be better. Okay, I'll read it. A hot surface at 100 degrees Celsius is to be cooled by attaching 3 centimeter long, 1/4 centimeter diameter aluminum pin fins with a given thermal conductivity to it, with a center to center distance of 0.6 centimeters. The temperature of the surrounding medium is 30 degrees Celsius. Now the surrounding medium is going to be something like air. Okay? And the heat transfer coefficient on the surfaces is 35 watts per square meter per degree Celsius. Determine the rate of heat transfer from the surface for a 1 meter by 1 meter section of the plate. Also determine the overall effectiveness of the fins. Okay, so let me sketch the system. I won't sketch the whole thing, obviously, but just to put a picture with what they've told us. The fins are separated by 0.6 centimeters. Let me try it over here. Hopefully that's not off the video. If it is, you've got the page there in front of you. The fins continue in both directions across the entire surface, which measures a meter by a meter. The fins have a length of, I think this is 3 centimeters. Can anyone read that for me?
Yeah, 3 centimeters.
3 centimeters, thanks. So 3 centimeters, and a diameter of 1/4 centimeter. Now this is basically aluminum. That's why they gave us thermal conductivity of 237 watts per meter per degree Celsius. The surrounding, in other words, the air around this, or oil, or whatever the fluid is around this, in other words, T infinity is 30 degrees Celsius. Okay? So whatever fluid this surface is transferring heat with is at 30 degrees Celsius, far away from the surface. Now the first thing, one more thing. The convective heat transfer coefficient in the fluid is 35 watts per square meter per degree Celsius. And I think that's all the data they gave us. The first thing you'd probably want to do is just work out the geometry part of the problem, because we don't know how many fins there are on the surface. So it'd be nice to know that. That's pretty straightforward. You realize that there's 0.6 centimeters per fin, so that's the spacing. And so what that suggests to you is that this is 0.6, what that suggests is that this is 1 fin per 0.006 meters. And so if we have a length of 1 total meter, then along this direction we must have 166.67 fins. Now I realize we can't have 2/3 of a fin, but I'm not worried about the round off, because I assume that this 1 meter area is something that's either extended or, if I'm off by a few fins, it really won't make much of a difference, okay? Because there's going to be a lot of fins in there. So that's the dimension. That's how many fins there are in the x direction. To find out the total number of fins, all I'd have to do is square that, right? Because there's going to be that many in this direction, that many in this direction, and just multiply those two together. That would tell me how many total fins. So basically that means that there's 27,778 fins per square meter. Does that make sense? Okay. Now, I would like to calculate the heat transfer rate due to the fins. And so that's going to be the efficiency of the fins multiplied by the maximum heat transfer rate from all those fins, right? So somehow I need to get the fin efficiency. What do you suggest that I do to get the fin efficiency? Well, there's a nice chart that we could go to, right? We go to that chart, we should be able to find a fin. What page did you guys say that was?
421.
421. Okay, so on page 421, you should be able to find the figure that was in the slides. What kind of fin do we have? Is it a triangle? A rectangle? No, this is just a round pin fin, right? So we have to use the curve that is for round pin fins. Notice that's the same curve as the one for the rectangular cross section. So, a couple of handy things. First of all, the area of a fin would be pi dl plus 1/4 pi d squared. When you calculate that, you get about 2.4053 times 10 to the negative fourth square meters. So that's how much area each fin contributes. The other thing we have to do, though, we have to come up with the, let's see, let's make a note over here. Sorry, 27,778 fins. Okay, per square meter. The other thing we need to do, though, is calculate the x-axis parameter. Do you see the equation there for the x-axis parameter? Looks like this: L plus d over 4 multiplied by the square root of 2h over k d. Now you have to be really careful here, especially if you have inch units, because it's very easy to mess up the units. So your parameter, your x-axis parameter should end up being dimensionless, but be careful when you're plugging in numbers. The length of the fin is 0.03 meters, right? And the diameter of the fin is 0.0025 meters. We have to divide that by 4. So far I have meters. I'm out of space on the video, so let me move down and multiply by the square root of 2h, where h is the convective heat transfer coefficient, so that's 35 watts per square meter per degree Celsius, divided by, I have to extend my square root symbol, divided by kd, where k is the thermal conductivity of 237 watts per meter per degree Celsius, and d is the diameter, which is 0.0025 meters. So we make that a multiplication sign that's more obvious. Now notice the watts go away, the degrees Celsius go away, that's not really a surprise, and the meters in the denominator go away, at least in this denominator, because this is meters over meters, so they cancel, and we're left with 1 over meter squared, square root. So we're left with 1 over meters, which will cancel with these meters. Okay, so those go away and everything's okay, but you have to be really careful. A lot of times what will happen, especially in English units, is students will forget that length and diameter may be in inches, well, I mean, it just depends. Sometimes the thickness also makes a difference. But what will happen is students will end up putting in feet or inches for h and k, and then d will be in thousandths of an inch or something like that. So just be careful with your units. You should always end up with a non-dimensional number. Anyway, plugging in all the units, let me get rid of all this, because all I'm going to do is just evaluate it. When I plugged in my calculator, I found that that number was about 0.3329. Now, if you're watching the video, you should pause it at this point. If you're not, what you should do is go to the figure and look up the fin efficiency. So the x-axis is 0.3329 or so, which is way too many decimal places to really think we could read it off that chart. But 0.3329, what fin efficiency do you think you would get? 845. 845. Anybody else?
87.
87-ish? Okay. I got about 88%. Okay. Now, I'm just going to go with that one mainly because that's what I used in my solution. But any one of the numbers you guys threw out there, 84%, that's fine. There's nothing wrong with it. We're just reading it off of this table or this figure, doing the best we can. Okay, so there's the fin efficiency. So we've got this piece of the puzzle. We've got the fin efficiency. Now we need the heat transfer rate from the fin's maximum. Now, how did that go? Do you remember? What was that all about? That was assuming that the fin was isothermal, right? So if the fin were actually all at one temperature, then the heat transfer rate would simply be the convective heat transfer coefficient multiplied by the area of the fin multiplied by the base temperature less the fluid temperature. Right? That's all it would be. And so if we plug in all the numbers, then this is, again, 35 watts per square meter per degree Celsius. The area of the fin, notice we calculated that a while back, right? We were just dealing with geometry at that point. So we calculated the area of the fin, and that's 2.405 or so times 10 to the negative fourth square meters. Again, I'm out of space, so let me multiply down here the temperature difference. The base we know is at 100 degrees Celsius, and the surrounding air is at 30. I think I forgot to write that the base temperature is 100 degrees Celsius, but that was given in the problem statement. So the degrees Celsius go away, the square meters go away, and we've just got watts. So one fin pulls off how many watts ideally? Well, it turns out it's about half a watt. Now, will the fins actually pull off a half a watt each or so? No, because they are not all at the temperature T sub B. So not all of this area is at temperature TB, so not all of it's going to give off heat at quite as large a rate. That's the whole reason that we went and calculated the fin efficiency. So now that we've got the fin efficiency and the maximum heat transfer rate, now we can calculate the actual heat transfer rate from the fins, and that comes out to 0.5186 watts. Now understand this is watts per fin, because I was dealing with the area of one single fin, right? Now that's not bad. It is actually a little more than half a watt. It was about 60% of a watt before, but because the fin is not all at the temperature of the base, T sub B, then the heat transfer rate is not quite as large as it would be ideally. So now we've used all this stuff. We don't need this anymore. I may need the maximum heat transfer rate a little later, but it's in your notes or you can go back in the video. So there's the actual heat transfer rate from each fin. Well, that's good, but we have 27,778 fins. So if you want to calculate the heat transfer rate from all the fins, you'll have to multiply 27,778 fins by the amount of heat transfer per fin. Okay? So when you do that, you find that the heat transfer rate from all the fins, let me make it clear that I'm talking about fins, all of them, you get about 14,406 watts. So that's the heat transfer rate from all the fins combined.
Per meter square, right?
For that square meter, right, exactly. Okay. Now, is that all of the heat transfer we're going to get? No, that's just the heat transfer from the fins. There's still a bunch of base area. Right? In fact, there's quite a bit because look, the spacing is 0.6 centimeters, but the diameter is only 1/4 of a centimeter. Right? So there's still a lot of base area that will transfer heat. How would we calculate that base area? Well, I did that somewhere here. Let me find it in my notes.
Take a square meter minus the
Exactly,
area of the
right. Take a square meter minus the area covered up by 27,778 fins. I did that somewhere here. I can't find it. I don't want to waste time on the video. But I calculated that the total heat transfer rate would be the heat transfer rate from the exposed area, that's the area that's not underneath the fins, plus the heat transfer rate from all the fins, which of course we already know this piece, but we don't know this. So I calculated the exposed heat transfer rate, or the heat transfer rate from the area without the fins, as, I'll just plug in the numbers so you can see it, 35 watts per square meter per degree Celsius. The base area, I'll let you prove this to yourself, is 0.8636 square meters. That's the area outside of the fins, okay? And so you should be able to get that on your own. But then the base temperature is 100, the fluid temperature is 30, this is degrees Celsius. Again, we just get watts. Anyway, that number comes out, let's see, let me do it this way. That number is something I'm going to put in right here, okay? So let me just write the result. It was, let's see, 2,115.9 watts. So then plus the heat transfer rate from the fins. You can see the fins are doing the majority of the lifting, right? They're doing the majority of the work. Even though they do not represent the bulk of the base area, because of all this area sticking up off the surface, even though that area is not 100% efficient, it still does a bulk of the heat transfer, or does the bulk of the heat transfer, which is not a surprise. That's why we put fins on surfaces. Anyway, so the total heat transfer rate is about 16.52 kilowatts. Okay, so that's the total heat transfer rate from this surface with fins. Now, that wasn't what we were asked. We were asked about fin effectiveness. So how effective are these fins? Well, the heat transfer rate with no fins would be equal to the convective heat transfer coefficient, all of the base area, which is just going to be a square meter now, multiplied by the temperature difference between the base and the fluid. Okay, so you tell me, what should I put in here for H? 35, right? 35 watts per square meter per degree Celsius. What should I put in for the area? 1 square meter, right? It's just the whole thing. What about this difference in temperature? What would it be? 70 Celsius, just like before. Good. So I'm not going to write that down. When you do it, here's what you get. You get about 334 watts. No, I'm sorry, that's wrong. I take that back. You get 334 plus 21, 15.9. When I performed the calculations, what I did is I actually used the area that was beneath the fins. That's the base area, so I misspoke. Okay, if we put in 1 square meter, we get this sum. Okay, so basically, here's the way to look at it. The base area that we covered up by putting fins down on top of it was only giving us 334 watts. So instead of giving us 334 watts, we put fins on it, now it's giving us 14,000 watts. Was it worth it? Absolutely, right? So we could look at this a couple different ways. The effectiveness, you could look at the overall effectiveness versus just the effectiveness. So let's start off with just the effectiveness, which is the heat transfer rate with the fins divided by the heat transfer rate without the fins. Just talking about the base area itself. It's obvious that they're extremely effective. 14,406 watts versus the area, or the heat transfer that the base area was giving us in the first place, all that base area, which was 334 watts, right? That effectiveness, I should have it here somewhere, is 43.13, which is obviously much larger than 1. So it's obvious these are doing a great job. But the overall effectiveness would simply be the heat transfer rate with the fins and the base that's still exposed, which is 16.52 kilowatts, divided by the heat transfer rate without the fins. Now the heat transfer rate without the fins is going to be 334 watts plus 2,115.9 watts, right? So let's do it this way. 0.334 plus, let's see, 2.1159 kilowatts, so that the kilowatts will go away. So plug that in your calculator, please. And let's see if overall it was effective to put the fins on this plate. I don't have that result in front of me, so I'll wait to see what you get.
6.8.
6.8? Sounds reasonable. Still much larger than 1. Yes, it was well worth it to put these fins on it. Any
So
questions?
6.8 times more heat transfer.
Right, 6.8 times more heat transfer from the overall plate. That's right. Now, there's 43 times more heat transfer from the base area that the fins sit on top of because of the fins. Okay, so the effectiveness of the fins themselves is this. The effectiveness of the fins on the plate, on the whole plate, is 6.8. Okay, any questions?
When we're calculating the transfer from the exposed plate under the fins,
Here? To get this number? Yes.
why do we subtract the area of the fins themselves from the exposed area instead of?
Because I understand what you're saying. Okay, we have already accounted for all of this area of the fin. All of that is right here, right?
Right, including the ends of the fin?
Including the ends of the fin. Yes.
So my question is, why do we do that rather than just counting that as part of the base area?
because this is literally part of the fin. So we put it with the fin.
Cause it's
Oh,
out.
wait.
Right. What you're saying is, it doesn't seem fair because this area would have been there anyway.
Yeah.
That's what you're saying. And that comes into the effectiveness. That question is answered by the effectiveness. Now, another way of looking at this, the fin does not necessarily have to look like this. It doesn't have to be a round cross-section. It could actually taper down. So we could actually lose that area, you see? So it could be that area technically is lost no matter how we look at it. It becomes fin area. And so not only that, but remember, a fin is not 100% efficient. Okay? And so the temperature out here is actually less than it would have been had it been on the base. That's another reason for not including it. Good question. Anything else? All right.